Welcome, guys. This is the first of the rotational dynamics video lectures. This is gonna be a long one. This unit is the biggest of our units, and because of that, it's gonna be a bit. Essentially, what we're gonna be looking at in this lecture is kind of looking at rehashing almost everything we talked about from momentum back to kinematics, but just imagining what if it was rotating. So a lot of the stuff you're going to see here, it does have a parallel to something we've already talked about. That being said, if you have your notes handy, we're going to go through here and fill out these notes together. So getting started here, the entryway into rotational dynamics is looking at uniform circular motion. All right, uniform circular motion. This is defined as an object that's moving in a circle at a constant speed. And that constant speed thing is kind of important because remember, speed does not take into account the direction of the object. So despite the fact this thing's going to be moving at a constant speed, the actual velocity of this object will be constantly changing as it changes direction as it travels through its circle. So we're going to kind of imagine that this is someone kind of twirling a ball around on a string in a circle. And it tells us the ball is traveling uniform circular motion. When time equals 0, the ball is at position 1, and we're going to put position 1 up here. Notice how the instantaneous velocity vector of the ball at position 1 points directly outward or blank. This is going to be tangent to the curve. So in our diagram, we're going to draw this. This is the radius of this circle. That's going to come into play a lot in this unit, is the radius of anything moving. And the velocity vector, the ball is currently traveling this direction. So this is going to be what V1 looks like. If we allow the ball to travel sometime, in number 3, it asks us to note how the velocities changed at position 2. So up here is where position 1 is, and over here is position 2. The old stuff looked like this. But at the new position, the velocity is still tangent to the curve. But remember, this thing is going on a circle, so the tangent line is going to continuously change as it does travel around the circle. So remember, the change in the velocity in a certain amount of time is called the acceleration. So anything that is going through uniform circular motion is undergoing some kind of acceleration. So we are supposed to look more closely at this acceleration. So if we were to actually, well, if you recall back into the kinematics unit, our equation for acceleration was simply A equals the initial, or V minus V naught all over the time that's elapsed. And we kind of need to figure out what this guy is here. So that right there would just simply be V2 minus V1. But because these are vectors, we kind of have to draw these things out. So since V1 is going in this direction, we would then, because we're subtracting our vector, this vector would be going the opposite direction for subtracting. So it would look like this. And this distance here would be delta V. That number is important, because once we figure out what delta V is, that thing can go in over here. So There is some like complicated math involved. I can go through that, but I don't think we need to talk about it right now. But it does take advantage of some like, similar triangles and some stuff. But the definition you kind of get out of that is when we are looking at uniform circular motion, our first equation is the acceleration, the centripetal acceleration, which I'll talk about in just a moment, is equal to the velocity of the object squared divided by the radius. This will still be in meters per second squared. This is called the centripetal acceleration. And the thing about the centripetal acceleration is it always points along the radius towards the center of the circle. And this thing here, centripetal, it literally means center seeking. That's where that name comes from. Number 6, note that if the radius of the circle increases, the centripetal acceleration will decrease because the radius is sitting in the denominator. And the same note, if the velocity increases, the centripetal acceleration will increase, but it will increase at a squared rate because that velocity is still squared. So just keep that in mind. If you swing something faster, it's going to have to accelerate at an even greater rate towards the center of your circle. We can also figure out what the speed of an object undergoing uniform circular motion by using a couple little things here. The first thing that we want to kind of think about, and these are the things that are going to kind of come into play in this equation. V and R, they make sense, radius, velocity. Capital T in physics is called the period. A period is how long it takes for something cyclical to repeat itself. So when we're looking at uniform circular motion, when an object goes one full rotation around the circle, that is called a period. And using our geometry stuff, we can kind of figure out here that the circumference of the circle is how far it's traveling. And because it's not that hard to measure the period of an object undergoing uniform circular motion, we can use a pretty simple equation. If you recall, our velocity is pretty much equal to distance over time. And because the distance in this scenario is going to be the circumference of our circle, we get 2 pi r up here. And the time element that's going to be involved will be the period, so that is capital T. So that equation is one we can now use to figure out the orbital speed, how fast something's going around in a uniform circular motion. And then 8, the last thing here we have frequency. Frequency is how many revolutions happen in 1 second. And if we take the inverse of the period, that will tell us what is the frequency. So for instance, if it takes something 3 seconds to do 1 period, the frequency will just be equal to 1 over 3, because it'll go through a third of a rotation in that 1 second. So those are some things we'll talk about here as we go forward. Let's turn the page. So, oftentimes we'll see a lot of this stuff happening, or we'll use a lot of uniform circular motion material when we talk about planets and bigger celestial bodies. So, calculate the orbital speed and centripetal acceleration of the Earth revolving around the Sun. The average distance from the Sun to the Earth is 1.496 times 10 to the 11th meters. So we do get R equals 1.496 times 10 to the 11th. Now, because we need To find the orbital speed, or the speed, we know v equals 2 pi r over t. We have r that's given to us. We know the period. And because we like to work in SI units in science, we have to do some conversions here. So the period of the Earth is just 1 year. But we want to do some converting here. So let's convert that 1 year into seconds. So getting started here. To match my notes here, we're going to use the conversion factor of 365.25 days equals 1 year. Years cancel. We have 24 hours in 1 day. Days cancel. 60 minutes in 1 hour. Hours cancel. And then finally, 60 seconds in 1 minute. And minutes cancel. So if we multiply this all out, we get 365.25 times 24 times 60 times 60. And we get the period is equal to 3.15. We're on the 6 times 10 to the 7th seconds, because these numbers are big. Let's just work in scientific notation. So to figure out our v then, we just need to plug in. So we get 2 pi times r, that's 1.496 times 10 to the 11th, divided by, nope, I'm messing this up. No, I'm good. Yeah, we're good. 2 pi. Divided by 3.156 times 10 to the 7th. So, a little bit of calculator work. There's the pi button. We get an answer. So the speed here should be 29,783 meters per second, which is quite fast. Then looking at our acceleration then, the acceleration equation looks like this, where we have AC equals v squared over r. So plugging in our previous answer of 29,783 squared divided by r would be 3.156 times 10 to the 7th. We're good to solve this then. So plugging this in, we get 2.73 squared. I just realized I made a mistake here. I plugged in my period and not my radius, so that radius should be 1.496 times 10 to the 11th. And with that correction, we get an acceleration of 0.0059 meters per second squared, which is why you don't really feel like you're accelerating much when you're going around the sun. That makes sense. We're going to pick up here with centripetal force business in the next video. So just scroll down and start the next one.